cycle between 5 megapascal and 10 kilopascal. Steam enters the condenser at 50 degrees Celsius, leaves as saturated liquid at the rate of 25 kilograms per second. The pump has an isentropic efficiency of 90%. So this one is kind of similar to ideal test. So here is just a simple reactor cycle. I mean, there is no reheat, no regeneration, just a normal one. But of course, not an ideal one also, because there is an isentropic efficiency of the pump. So the full pressure limit. So as standard, part A asks you to draw this, so you just draw. So 1 to 2 is similar. Three, 4. So if you only read the question first part, you wouldn't know whether the turbine is an isentropic turbine or a fluid turbine. But if you continue to read B and C, so C asks for isentropic efficiency of the turbine. So meaning the turbine itself is equal to the turbine. So we have this as well. Okay, so center medium building So B determine the temperature of the steam entering the turbine if the net power output of the plant is 25 megawatt. So you need to find out P3 if net power output of the plant is 25, and also if work net is equal to 25. Okay, so with this, we still need to do things one by one. Alright? So we look at step 1 first, because you are given work net, which is not really work output P. So you still need both of them. So we look at step 1 first. So what do we know about step 1? So steam enters the condenser at 50 degrees Celsius and leaves as saturated liquid. So we know that T1 is equal to T4 in this case. You will just look at the expression at all. So this is 50 degrees Celsius. And it leaves as saturated liquid. And we also know we have explored as well. Wait, we cannot use 50 degrees, sorry. We should use T1 equals to 10 kilopascal first. Sorry, that one. Okay, so let me write down information here first. So yeah, I jump a bit so we complete that. So between 5 megapascal and 10 kilopascal, so we do have the two pressure limit. So we know that T1 equals to T4 is 10 kilopascal. We know that T2 equals to T3 equals to 5 megapascal. And we know that T4 is 50 degrees Celsius because it enters condenser at 50 degrees Celsius. And at state 1, saturated liquid, and mass flow rate is 25 kilograms per second. So what you saw I did just now is I jumped to conclusion without really reading the whole thing. So that's what students usually do also. I didn't do that intentionally, but then yeah, that was a mistake. So still again, when it comes to an actual cycle, do not assume anything. Read properly everything, write down, then you will see what are the things that we have. Okay. So T1, 10 kilopascal, saturated liquid, so we can also find V1. Right, then after that, we can move on to state 2, where we say that H2S minus H1 is equals to P1, P2 minus P1. And we know H2 minus H1 over H2S minus H1 is equals to isentropic efficiency of the pump. Wait, the line H2S H2. So from here you can get H2. So state 3, we only know P3 is 5 megapascal. So we don't have enough information here. So we can skip this first. Then we move on to state 4. So state 4, we have new information. We know P4 is 10 kilopascal. We know T4 is 50 degrees Celsius. So based on this, you can find H4. It should be a superheated vapor. So it doesn't matter what state it is because we know the question directly asks you to right, but the table should be for the stated vapor table. Okay, so far for you at least this is at least the minimum that you should reach. Okay, because these are all just looking for all the technology based on the properties that you have. Alright, so now we cannot say not really cannot say, but at this point we still cannot use this yet. S3 equals to S4S. Right? Because it is S3 equals to S4S. We also don't know anything about 4S. Right, we don't know anything about state 4S, so you can't really make use of that because you cannot find S4. Because S4 and S4S are not the same, and they are not related. Okay, so now we look back at what do we have. Alright, so what does the question give you? So the question actually gave you work next, right? So which is 5 megawatt, and this is equal to work out minus work in. So you actually can find H3 from here, which means this is 5,000. Okay, 5,000. So mass flow rate. The workout is H3 minus H4. Minus H2 minus H1. Meaning the work in that you can find from state 2. So in state 2, you can actually just find the work in first. And that method, because it uses H2 minus H1. So here in this case, you have H4, you have mass flow rate, you have H2, you have H1. So from here, you can find H3. So you can always look at what you have. So what the question gives you and what you have here. So once you have H3, then you can sub in here. So here you know what is H3, right? Then you can find T3 through interpolation. So this T3 value should be this, which is given in the classic the classic solution answer. Here's the one. Then we look at C. C asks for isentropic efficiency of the turbine and also thermal efficiency of the cycle. So, isentropic efficiency of the turbine, we know that this equation is H3 minus H4S, H4 over H3 minus H4S, and thermal efficiency is just work net out over QE. So thermal efficiency shouldn't have any issue, because here this is just H3 minus H2 over, whatever that you found at the top there, or maybe you can just use this over and flow rate H3 minus H2. So for this, you need to find H4S. So for H4S, we say P3 equals to 5 megapascal. H3, we have this, right? So once again, you need another interpolation to find H3, so S3. And then we say P4 equals to 10 kilopascal. S4S equals to S3. So from here, business as usual, you find X4, then you can find H4S. So any question here? If not, I'll move on to question 2. So question 2A is another of the you need to find the application for four-stroke and two-stroke question. So let's see what the question was. So actually this question is quite similar to the other question. So the other question was purpose is ski. This is ATV. Okay. So once again, you need to choose between both four-stroke and also two-stroke engine. So as an engineer, you are tasked to advise the client on whether a four-stroke or two-stroke engine is better suited for an ATV design for which use. So first criteria here. So we will encounter varying terrains. So it requires frequent short bursts of power. So maintenance, once again, is not major concern. Sustainability is important. Okay, so basically you need these three. That's the important part here. So analyze the advantages and disadvantages in terms of efficiency, power output, simplicity, and also environmental impact, and determine the most suitable choice for the client. So first thing, we look at efficiency. So for efficiency part, of course, the better engine is actually the four-stroke engine. So typically, exhibits higher thermal efficiency compared to two-stroke engine. Better fuel economy. So second one, power output. So this one is actually, we will actually give this to two-stroke engine because it offers a higher power to weight ratio. Because now we are just talking about a small application. And also quicker burst of power, and maybe let's say quicker acceleration. So this was actually mentioned in the question as well. Due to power strokes occurring twice as often. Because so two-stroke engine will actually provide you more quick short bursts of power because it only needs one cycle for one power output compared to four-stroke. So simplicity, obviously this one I think I need to say name. This is also two-stroke engine. So this generally has fewer moving parts. Also easier for maintenance. And lastly, environmental impact. This one definitely is the four-stroke engine. The four-stroke engine has better emission or fewer emission. Cleaner or more complete combustion. Because we know that 4-stroke engine, the combustion will be more complete because compared to 2-stroke engine, where sometimes you will have unburned fuel as well, so the combustion is also not as clean. Okay, so now that we have listed out all 4 of the criteria, then now we need to choose, right? We need to make a conclusion on which one to choose. So based on the criteria here, you know that, so this thing means what are the important ones? The ATV requires frequent short bursts of power, right? So power output wise, this will be important. So 2-stroke engine score 1 basically. So maintenance is not a major concern. So the simplicity part actually doesn't really matter as much. And sustainability is key, so we know environmental impact is important. So if we only look at these two, we have 1-to-1, so 4-stroke engine. So which one do you choose? Actually, I think more priority is efficiency is also part of sustainability. So then 4-stroke engines are 2 major ones on this one. Because if you only say simplicity, right, you can also say about efficiency is also not part because they didn't say anything about it. But technically speaking, efficiency is part of sustainability because that you high efficiency you are using less fuel. So efficiency is also part of the main criteria. So meaning 4-stroke actually has one more main criteria compared to 2-stroke engine. So conclusion. Yeah, please give me a conclusion also when you write this. But of course, let's say for like in this case I give you 10 marks. So by listing down all those 4 correctly, you will have already gotten 10 marks. So the conclusion is the last 2 marks. So this one you just conclude based on the criteria. So considering, let's say the need for sustainability, we can let's say need for so efficiency, let's say fuel efficiency, and environmental impact. For stroke engine, is the preferred choice. As maintenance is also as maintenance is a minimum concern for the client. So you can. So when you conclude, yeah, basically just like when you write that is what you look at what are the criteria the question gave you, then you conclude based on that. Then you can be sure to choose. So let's move on to question 2b. So question 2b, we are back to engine. Okay, we have always taken engine, but we are back to the calculation part. So you can see this question is quite basic here. So we have a 4-stroke, 4-cylinder engine with a bore of 120 millimeter, a stroke of 350 millimeter, which operates at 800 RPM. At full load, the BMP is 3 bar, and the top arm is 0.5 meter, so 0.5 meter. Okay, so you are given a Morse test this time, and the cylinder are cut in the order 1, 2, 3, 4 with corresponding brake loads of 550 Newton, 520 Newton, 508 Newton, and 523 Newton respectively. So for the engine, 1, calculate the brake power, 2, the mechanical efficiency of the engine, and 3, the mean piston speed. So we have BMP, you can calculate the brake power first. This is brake power times 2 over ALMN, or in other words, maybe we say over the set volume. So BP times 2 over ALMN. So you sum in everything, you will be able to get BP. So, but of course, in this case, one thing is your BMP, they give you 3 bar, right? So change this to 300 kilopascal before you start the calculation. Okay, so to calculate the mechanical efficiency of the engine, so we need to make use of the Morse test in this case. So for the Morse test, you can see that the result output here is actually the brake loads. So what you need to find is actually the load, the total brake load first. Okay, so meaning this one, the VP we know is equal to 2 pi and T, and then 2 pi and WR. So this W is the one that, this W will be our capital B. So because when we do Morse test, we like to write this, right? Name this one. So I2 is B minus B2, I3 is B minus B3, and I4 equals to B minus B4. So for Morse test, we like to write this. So meaning we need to find out what is the capital B here. And in this case, since B is given in terms of Newton, which is the load, so this is your B. So from here, you calculate W first. Because with R, you have the empty speed, the 2 pi, you have just found brake power from 1. So from here, you can find the W, which is also equal to B in this case. So after that, you sub the B in minus each of the B1, B2, B3, B4 respectively. So from here, you should get I equals to I1 plus I2 plus I3 plus I4. So your I here is also in terms of Newton. Then mechanical efficiency is just B over I. The last one, same thing, mean piston speed. So this speed is just the N in terms of RPS times 2 times L. Those are what I showed you before. Alright, so yeah, nothing too special here. We look at question 3. So consider a power plant with regenerator. So this time we have a regenerator, which operates on a simple Brayton cycle using air as a liquid fluid. The cycle has a pressure ratio of 9 and a flow rate of 15 kg per second. The maximum and minimum cycle temperature is 1027 degrees Celsius and 27 degrees Celsius. The compressor and turbine each operate with isentropic efficiency of 88%, and the regenerator has an effectiveness of 0.9. Okay, so yeah, I think this one I can just write down. Okay, so as usual, you need to sketch TS diagram. So since this is just a simple Brayton cycle with regenerator, of course, we can just go through two of these ones first. Okay, so 1, 2 has, then 2, 3, 4S, and 4. So we also, you have a regenerator. So the regenerator should go something like this. So for the regenerator, the ideal line should come from actually both lines. Should come from the 4, okay, not 4S, because that is the actual case. So regenerator should come from this, but of course this is not the actual line. The actual line should come here. So this is the 5. That's all this. So the 5 should come down slightly. Okay, maybe not so clear here, maybe that go again. So something like this. So now, if you want to, you can also draw this line up, but I usually don't make use of the throughout line. So if you don't draw that, I'm also okay. Because there should be another throughout line here. Or we don't really make use of that line usually, because I don't really use throughout for this question. So it's okay for you not to draw that. Okay, so let me write down what are given here first. So R is 9, mass flow rate is 15. Maximum temperature and minimum is, so the maximum temperature T3 1027, so this is 1200 Kelvin. Minimum is T1 300 Kelvin, and this is 0.9, and T equals to, and C equals to 0.88. So these are given to you. So B, by assuming variable specification, so this is a variable specification question. Determine the enthalpy of the air at each stage of the cycle. So this one, I think you know how to do, right? So you know that T1, so let's say we say process 1 to 2, or state 1 to 2 over there. T1 is 300 Kelvin. So based on the table, you can get H1. You can also get PR1. So after that, we say PR2 over PR1 equals to R. From here, you can get PR2, then back to the table, you can get H2S. Okay, this will be H2S. So whatever that you found using this or the isentropic equation, they are always the S version, not the actual version. So that after that, we know that MC is equal to H2S minus H1 over H2 minus H1. Then from here, you can get H2. So you don't really need to find T2 because you don't really need to in this case. Just to H2 will be fine. Then process 3 to 4, you will repeat the same thing. We know T3 is 1300 Kelvin, so you find H1 as a H3, you find PR3. Then PR3 over PR4 is R, so you get PR4, and then you get H4S. After that, and T is H3 minus H4 over H3 minus H4S. From here you can get H4. So this way you can get all the enthalpy. So this one pretty straightforward. Okay, so now we look at C. So C determines the net power output produced by the power plant, the back ratio, thermal efficiency. So our standard things are. Okay, so C you need to determine net power output first. So for net power output, we don't really need to care about the regenerator yet, because the regenerator only affects QE. It doesn't affect work out or work in. So here you can do work out minus work in first, which is H3 minus H4, H2 minus H1. So backward ratio, you also don't need to care about it because backward ratio is just work in over work out. Thermal efficiency, then yes, because thermal efficiency is work net over Q in. And your Q in is actually so what is your Q in this case? H3 minus H5. So you need to find H5. So H5 will be from the effectiveness equation. So effectiveness will be H5 minus H2 over H4 minus H2. Then here you can get H5. So calculate the effectiveness based on how much heat you can regenerate. So the regenerated heat is from 2 to 5. So ideally it should be from 2 to 4, but of course we will have some heat loss along the way, so we become H5 instead rather than H4. So the H5 minus H2 over H4 minus H2. So there's one more question. So these say explain how the inclusion of a regenerator affects the thermal efficiency of a simple Brayton cycle and provide the reason behind this. I think this one you can try to answer yourself lah. Basically regenerator, you make use of the waste heat. Regenerator basically you make use of the waste heat to heat up the air first before it enters the combustion, so it reduces Q. Basically, that is what you need to say. So we reduce the energy wasted and then you reduce the energy, the heat in, and thus the thermal efficiency is increased. Pretty much that. Okay, so we have one last question. So that Brayton cycle question is really just that to be marked on. So if you have this question, make sure you score, okay? The part that you probably don't score is the explanation part. Not very hard. Okay, now question 4. This is the question that this is the hard question for this semester. April and May, it's May 2024, so have to say that. Yeah, he cannot solve it. He will wait for me. Because he tell me he cannot do chemistry, so he wants. Okay. So yeah, most of the students from this, because this batch usually they score quite well. And this is the only question that they usually cannot score. This is the question that most of them cannot score. The rest they were okay. 1, 2, 3. Because as you can see just now, so 1, 2, 3 wasn't too hard. Maybe one a little bit tricky with the power. But otherwise still quite standard. Alright. So question 4. Actually A is in the tutorial also lah, but I added it a bit here and there to make it a bit longer. So let's read this. So a rigid tank with a volume of 1 meter cube. Let me see if I have spacing. Okay, is divided into 2 equal compartments by a partition. So you can see just from the first question you know that this is actually quite like your tutorial question in a way. So you have a tank. Total volume is 1 meter cube. So we divide it into half. 2 equal compartments. So half, exact half. I know it doesn't work it, but it is exact half. So one compartment contains N2 at 10 degrees Celsius, 100 kilopascal. The other compartment contains AR at 20 degrees Celsius, 200 kilopascal. Upon removing the partition, the two gases mix together. So during this mixing process, the system absorbs 8 kilojoule of heat from surroundings. So, still heat. Determine the final mixture temperature and the final mixture pressure. You may consider both N2 and IR to have the same properties as they are at 300 Kelvin, and the ideal gas constant RU is 8.314. So you are given the universal gas constant 8.314. The respective gas property refer to table A2. Then you can get this question. So this question actually is not a tutorial actually. It is there one of the tutorial questions. Okay, so what do we need to do first? What can we do first? Find the mass. Now, okay, so we find mass first. Okay, so we can find N2 and MR first. Based on their respective PV equals to MRT. So T1, P1, RT1. This one technically also P1, PV1, RT1, but this is for the N2, this is for the AR. So P1 question gave you the P, gave you the T, you know each of their B. R you can get from the table for AR and also N2. So you can get their mass first. I mean, yeah, then you can get the answer, right? Okay, so then what do you do next? Actually, why do you need the mass? You want the parabola mass? How long? You can do that also. Here I didn't do that, but you can get MM from here. Because this will be N2 plus MAR over the total N, right? So meaning you still need to find the N if you do this. But actually the N is the composition no, the ratio is the fraction is equivalent, but you cannot say N is volume. because N is mole. Right, so actually you can use, yes. Heat capacity. Okay. Heat. Yeah. So yes, okay. You will need to remember that we are still doing thermo here, right? So what system is this? This is a closed system. Even if you remove a partition, it's still a closed system because everything happens inside. So meaning this whole thing, the energy transfer here is equals to delta U. So what we have here is QE. There is no work. And here will be MC V delta T. So we can split this into two. T2, or rather T of the mixture minus T1 plus NCV. T of the mixture minus T1. So this is for this is for N2, this is for AR. Because their final temperature is the same. So you found the mass just now. So each of the mass, so you're not wrong. You need to find each of the mass. Then after that, so here you put in all the values, you can get Tm. So this is the final temperature. Okay, so this is the final temperature, but you still need to find the final mixture pressure. Yeah, so we can go back to the ideal gas equation. Now the issue here is this. We have this, we have this, we have this, so you need to find Rn, right? And to find Rn, you need Nm. So it means that we still need to find the mole, number of mole, total number of mole here. So don't forget the last thing that the question gives you. And technically speaking, if you find Nm, it's an extra work. Why do I say that? So now we need to find the number of mole, right? So PV equals to MRT has another version. To nRT. Right? This one. So based on this, you can find NAR, you can find N2. Right? So you can also use this version. So if you use the universal gas version, then you don't need to find the molar mass of the mixture. So you can save steps here, one step. Yeah, actually this one just tedious me because you need to repeat this to find the mass, then repeat this to find the mole. So don't forget that solving things in terms of mole is always easier compared to mass. So possible just to use like mole. Like I said, 3 steps here because my solution here identified mass, I just took the answer. So we should be the first step. For the mass. Mass still need to find because otherwise, right, you cannot do QE. Unless, okay, technically speaking, you can do QE, but I don't think you have the table because the table gives you CV, but not CV bar. If you have CV bar, then you can skip the mass totally. But I don't think the table has that. The CV bar is based on mole, not mass. So we are left with B. Okay, so everyone understand what we are doing here? Okay, then let's look at the last section. So question 4B. Okay, so sample of petrol which only consists of carbon and hydrogen is burned with dry air and dry analysis. So the product shows 12.04% CO2, 4.91% CO, and 3.05% NO2. So this is a question where we flip the question where you are asked about you are given the product. So dry analysis, we have Y CO2 12.04%, Y CO 4.91%, and Y N2 83.05%. So one, determine the ultimate analysis of the petrol. So we need to find out what is the composition of the petrol. This petrol that we know is that the only thing we know about it is it consists of carbon and hydrogen. So just like the tutorial, we assume something first, so it only consists of carbon and hydrogen, so we don't know what the composition. We write this down first. So since this is burnt with, as usual, so O2 plus 3.76 N2. So we know that. So what do we know here? We know the dry analysis. So let's assume 100 kilomole of dry product. You want to assume 1 kilomole also can. So as usual, this one is up to you. You should get an answer. So when we assume 100 kilomole of dry product, meaning we get 12.04 CO2, we get 4.91 CO. Don't forget you have H2O in the product, even though we didn't mention it because it is a dry analysis. So you still have a H2O. That's why the 100 kilomole is for dry product, it's not for product. And 83.05% and so from here, we can start balancing. So if you balance carbon, you will see that X is equals to 12.04 plus 4.91, and you get 16.95. We balance H, Y is equals to 2B, nothing else. Then we balance O, so 2A is equals to 12.042 plus 4.91 plus B. So from here you can get B is equals to 15.186. Anyway, now yeah. So then we go to N2. So N2 is 3.76A equals to 83.05. So here this gives you 22.09. Then B will give you 15.186. Then you come back here, Y gives you 30.37. So if you assume 1 kilomole, then everything is due 1 something. But of course, we are actually not done yet. We know the composition of C to H now, but what the question is asking here is actually the ultimate analysis. So what is ultimate analysis? So ultimate analysis of the petrol. Mass what? You want the mass fraction. You want analysis of the petrol in terms of mass fraction. So meaning you want MF of C as well as MF of H. So we know that the number of mole of C is 16.95, so we convert it back to mass. And the total over the total mass. Okay, maybe let's write it properly first. So this should be M of C over M total. So meaning 16.95 12 over 16.95 12 plus 30.37. So for H, same thing, over M total, you want 30.37 over 16.95 12 plus 30.37. You should get about 87% here, 13% here. So the total should be 100%. So ultimate analysis is the mass fraction, like the analysis of the substance based on mass. Okay. So lastly, air fuel ratio by mass. So air fuel ratio here can find very easily based on mass of air over mass of petrol. So mass of petrol again is just the M total. So this M total and air, the answer is that. So it is 22.09, 29, and 4.76. So you should get the air fuel ratio here. And lastly, you need to find out the percentage of theoretical air used. What do you do here? You want percentage of theoretical air. It's actually opposite of what you do. So I always mention, right? Let's say if I tell you you have 200% theoretical air. Or rather, or you have 100% excess air. What is that 100%? What is that 200%? You cannot find them if you don't find stoichiometric. Stoichiometric is the 100%. It's the original amount. Meaning, you need to find the stoichiometric amount. So, for theoretical amount of air, so the stoichiometric equation is this. So now that you how should I say this? Okay, you can directly use the 16.95 value and the 30.37. But that is a very large number. So my answer here, what I did here is actually from the 87% and the 13%, right? I convert it back again to mass. So meaning I assume back maybe 1 kilomole of fuel, then I convert that. But then that one is not really necessary. So what you can actually do is you usually, so if you don't find a big number, you can actually just use this one also. You assume complete combustion. Okay, so from here, yeah, actually all you need to do is just balance that. So you will see that x is back here 16.95, and then h, y is just 13.37. Then O, you can find ATH. So you only need to find up to ATH. Then the percentage of theoretical A is just A over ATH. So in this case, ATH should be a larger value compared to A, because you have incomplete combustion in section 1, because you have CO in the product. So your A, the ATH equal should be a smaller value one. Should be a larger value, ATH. Yeah. What I did here is because I don't find the number. I find again the new number of O, but it doesn't matter. You don't need to because it complicates things a bit. You can just use that for value. Same answer. Okay, so yeah, the percentage of the return you get 90%. Okay, so we can try this out. So like I said, if you can do these two parts here, you can understand fully. I don't think exam you will have much issue. Of course, there are probably still different things there, but in general, the basic concept are the same for these two parts here.
啊，那个不会做啊？对，再好呢。这个第4课它有一边是算2道币的，只是讲没有出啦。这个。
对，他们是有来的，我去那里，他们去那个他们拍摄老师的唱戏，
准备他睡觉了，他走掉了。